All right, so we've done statistical thermodynamics already for the individual states. We talked about translation, rotation, vibrational motion. We even went through the spreadsheet and showed that those equations will reach the classical values of just billiard balls in space bouncing around in a room and getting them hot. And so this connects quantum theory to bulk properties. And so the statistical part is, like you know, with statistics, sort of stochastic process. You throw random molecules at a set of energy levels and you get certain populations. And then this thermodynamics part connects it to the energy and bulk properties that you're familiar with, like energy, entropy, enthalpy, Gibbs energy, and so on, and even the equilibrium constant. So we're going to be talking about these two things in today's lecture, but we're going to continue next on Monday and Wednesday on the others, entropy, enthalpy, and so on. Yes. Which one? Oh yeah, that's this. I call it U shag and K. So U shag is all of these pieces. Yeah. And so it's all of the energy functions that you've heard about so far. So that's my shorthand, U shag and K, and you know, so we'll do these problems like from beginning to end, all the way down to the equilibrium constant. Yeah, how weird is that? No, that's cool. Emphasized in this lecture. Okay, so I don't know what font that is, but sometimes printing to PDF, it'll like go crazy. Is it bad? Does it say anything bad? Okay. Yeah, so the font, I don't know what happened with the font, but that's crazy. Glad it didn't like insert something offensive. Yeah. Wouldn't that'd be terrible. Yeah. Okay, so we just used this equation. And I say use this formula only if you can count the number of energy levels. So like if I give you a 2-level problem and ask you to calculate the energy, this is the equation you use. Okay. So you would sum those energies, do the partition function, so on. We've already done those problems on the homework, but this is the expectation value that we saw earlier. Now I did this in a spreadsheet for a complicated molecule, and this equation works. So it doesn't just work for small systems; it works for realistic systems too. But I was using the spreadsheet to do 100 values, and you're probably not going to do that by hand. But once you have that internal energy, then look at all these other equations. You can use that internal energy and in the partition function, and you can get the entropy. And then once you have the entropy and the internal energy, you can get these other values here, like the Gibbs energy. So the entropy goes here, and the enthalpy goes here. And where do you get the enthalpy? Well, from U and temperature. And from the Helmholtz energy, you use the entropy to give that piece and the internal energy there. So you see how it all builds. You start with the partition function, and then you can get the internal energy, and you can work your way all the way through. So we can calculate all of these thermodynamic values. Now, equipartition at high temperatures, it talks about the high temperature limit. I probably should use the word threshold, right? When you're above a certain temperature and higher, you have equipartition. And this is the energy for translational motion. And this is, again, 3 degrees of freedom. You get half of an RT for each of the degrees of freedom. So X, Y, and Z for sort of unidirectional motion. So that word unidirectional is important. So for every uniform direction, so unidirectional in X, Y, and Z, there's no restoring force making them come back. That would be vibration. Okay. And then for rotation, that's also unidirectional. You're rotating around X, around Y, around Z. You get a half an RT for each of those. Now, vibration is bidirectional. It's a restoring force, so it goes forward and backwards. And so for that case, you get 2 halves. You get a half for one direction and a half for the other, and so it adds up to 1. So for each activated vibration, you have 2 halves RT or just RT for each vibration. And these would be the equipartition or classical values for all of those, the bulk values for all of those degrees of freedom. And so we're going to be calculating these for a lot of different molecules today and atoms. So this is your other decision point. You know, if you're dealing with moles of particles, or if you see the word equipartition or high temperature, or even room temperature in most molecules, if room temperature, so I'll say room temperature. So room temp, use this for the top two. I'll say small. So small molecules at room temperature, we have the equipartition condition for those top two. Now for electronic energy, we're not going to be putting any energy into the electronic states. If we were to totally populate all the electronic states, we would be populating antibonding orbitals and the molecules fall apart. So we can't get to equipartition of electronic states, or we would have a zero bond order and we wouldn't have a molecule. So that's how things decompose. So as like a candle, the wax migrates up the wick and gets into a really hot zone, and the vibrations of the molecule and the electronic states of the molecule start getting excited, and it rips the molecule apart. And then it's the gaseous byproducts of that decomposition of these big waxy molecules that burns. And so there's like a pump too. So that molecule no longer exists. It's being broken apart. And so then the wet wax fills in the gap that's left behind from the molecule that decomposed. So we're breaking those molecules to pieces using heat. So let's look at the heat capacities. These are your simple derivatives, right? You're going to take the derivative of U with respect to temperature. And so for translational motion, we have 3/2 nR. For rotational motion, for a linear molecule, it's 2/2 nR, because we only have 2 degrees of freedom, 2 rotational degrees of freedom. In both the energy and in the heat capacity. Okay. For a nonlinear molecule, we have 3 rotations. And then for vibration, we have to add a variable here, A, where A is the number of active modes. So as the molecule gets bigger, and even that we saw in our spreadsheet example that the vibrational line for a couple of the vibrational frequencies was still 1 for the partition function, but the other one started creeping up. And so it started accepting excitation at 300 Kelvin. And so that mode was becoming activated. It wasn't fully activated to give the equipartition condition, but it was beginning to be activated. So when T is over 10 times the vibrational temperature, then the mode becomes active. And so here's our total. And we have the sum of the heat capacities. So the total partition function is the product. It's all of those Q's multiplied by each other. But in terms of energy, it's a sum, and in heat capacity, it's a sum. Okay, so we'll practice with this with a Kahoot. Okay, and so remember, these are I'll give you a hint on the Kahoot, right? These two here are only available. Let's see, translation is for everything. All, and then for rotation, only molecules. And vibration, only molecules, right? So like if you get helium or argon, there's no vibrations in argon. And there's no rotations in argon, right? So so anyway, with that hint, let's go take a Kahoot. Let's see, let's do this one. There you go. Now this is going to be a little tough for you guys because we haven't practiced a lot with these, calculating these heat capacities. So. Nice to be creative. Yes. Is that a bike helmet? What is that you got on there? There we go, top hat. All right. So. All right, let's get started. All right, what's the room temperature heat capacity for a mole of helium? So you may have to, I don't know, you don't have any pencil and paper, but you may have to like think through how many of these halves, R's, and stuff you need to add together. Not so much for this one, but in the future. Okay. Okay, very good. So the ones that hit red didn't notice the T. So that's the energy for but the heat capacity is the derivative of that. So it's just 3/2 R. And think about the units of R. So it's joules per mole per Kelvin. So it's energy per Kelvin, just like the Boltzmann factor. Okay. All right. All right, what about 4 moles of helium at room temperature? So if it was 3/2 R for 1 mole, what is it for 4 moles? A little bit bigger, but it's even spread across. All right, good job on the reds. Yeah, so you have 3/2 R for 1 mole, and then you multiply by 4. 4 over 2 is 2. 2 times 3 is 6, so we have 6 R. Okay. All right, a little mix up there. Sorry. She's like, surprised yourself. All right, what's the CV for 1 mole of carbon monoxide at room temperature? Small molecule, okay. So you got to take into account the translations and the rotations. And since it's a small molecule, probably not the vibrations. Okay, so you leave that one off. If you'll need a pencil, work your way through. We got a couple of thinkers here. I typed in carbon monoxide to find an image, and it said carbon monoxide detector. Okay, good job. So yeah, 3/2 for the translation, and then another 2/2 for the rotation. So that ends up to be 5/2. So that's 1 mole of CO, room temperature. We're not counting the 1 vibration. That would make it 7/2 R if we calculated the vibration, but it's not active at room temperature. Okay. Ooh, on fire. All right, so now we got water vapor. 1 mole of water vapor. Okay, small molecule, so probably not going to do the vibrations, but we've got translations and rotations. Are y'all debating?
No, my phone turned off. I got scared.
Oh. Yeah. All right, one more. Okay, a little bit of a spread, but still the majority wins, and got it right. Yeah, 3/2. So it's 3/2 R for translation, 3/2 R for rotation. You add those together, you get 6/2 or 3 R. So this, I mean, it's convenient to write it like this in terms of R, because then you just calculate it using the gas constant. So it's 3 times 8.3145 joules per mole Kelvin. So for every Kelvin, you get that many joules per mole if you want to pull the energy out. If you want to raise the temperature, you put that much energy in to get it to go up 1 Kelvin. Okay, and every substance has a different slope, a different heat capacity with its energy. Okay. All right, so this is the last one here. Good job. What's the maximum for water? Okay. So the maximum now would calculate, you need to calculate the vibrations, right? So we have the translations and the rotations, now we have the vibrations. So put all of those together, what's the maximum heat capacity for water vapor? I don't know why it doesn't play the music in here. It plays it in the other classroom. Okay. 2 people. Good job. So how'd you come up with that number? All right. It's the 3/2 for translation, 3/2 for rotation. And so that ends up being 3R. And then for each vibration, you get another R. So we're out of the halves, right? So it's 3 from translation and rotation. And then you have vibration number 1, 2, and 3 for a 3-atom molecule. Add those together, you get 6R. Okay. Good job, Zach.
Oh, nuts.
Okay, yay, good job.
They said you tried.
All right. Good times. Let's see what we got here. Let's look at some real heat capacity values. Let's see. Got some crazy stuff going on with my windows. Turn that off. Okay, excellent. All right, so that's the application of that equation there, you know, for translation, rotation, and then vibration. And then this is what happens when you have dissociation. So here for, say, a diatomic molecule, it starts out with 3/2 for translation, and then it adds up to 5/2, and you keep adding the temperature, and you might start getting some vibrations, and then it decomposes, and now you have 2 atoms with just translation. So you have 3/2 for each atom now, and so this would be the heat capacity for atoms, and that typically is what happens when things decompose. Okay. So let's look at some data from the CRC, and this is pretty cool. Notice for the heat capacity at constant volume, whether it's argon or mercury, it's the same. Isn't that cool? Doesn't matter what mass, you know, at all. That's the translational heat capacity of argon vapor or mercury vapor. Okay. Now there's something strange going on here with aluminum and uranium. Okay. Well, let's look at, I thought that was the next one to be revealed, but let's look here. So this is the experimental values, 12.486, and here's the theoretical values. 3/2 R is 12.47, right? And, you know, for all of these, the aluminum, uranium are coming in pretty close to those values. But let's look at the diatomics. So bromine, CO2, CS2. The theoretical values are 3/2 R for translation, 2/2 R for rotation. So this is the theoretical value. The equipartition value is 20.786. And then here for bent molecules, asymmetric molecules, it's 3/2 R for the rotation. And so it's close to 25 for the theoretical values. Now here's the experimental values. So aluminum and uranium are a little strange. They're coming in a bit high, okay? And so that has got to have something to do with the small difference in their electronic energy levels. So what does aluminum have, right? It's got one electron in the p orbital, and there could be some spin orbit coupling with the really small energy level spacing there. So even though we said we don't take into account electronic excitation, in certain situations it might be there, okay? But look at our assumption. Our assumption is that that's not there, and it's a good assumption for most of these atoms, okay, and for the molecules too, okay. For the diatomics, it's pretty good, but these are some pretty large atoms, especially sulfur and bromine. These are coming in higher than the equipartition value, so there must be some vibrational excitation taking place in those molecules. Okay. And then here for the bent molecules, you see there's a huge, or nonlinear molecules, there's a huge variety in their heat capacities. So this would be the theoretical value with no vibrations, right? I don't know how to say that, but I'll do it vertically, no vibe. And obviously these have some vibrations, right? So let's look at how much of their vibrations or other kinds of properties is coming in. So these don't have any vibrations, and so there's no percent active vibrations there, but they're different by a couple of joules per mole Kelvin. And so this is clearly going to be some small amount of electronic excitation. Okay. But here we definitely see some vibrational excitation. We have 4 vibrations in CO2 and 4 vibrations in CS2. And the smallest energy vibration is the bending mode. And so for the carbon dioxide, that bending mode is not very excited. Only 24% of those vibrations is active. But in the CS2, both of them. So the bending motion in this direction and the bending motion in that direction are active at room temperature. And that's where this extra 16.3 joules per mole is coming from. Now let's look at water. So around 1% of water's vibration is active, because it's 25.29, not 24.9. But look down here at carbon C60, 33% of its vibrations are active. So yeah, the theoretical translation and rotational heat capacity should be 24.9, just like all the others, but its heat capacity is 503. Okay, so neglecting the vibrations in a molecule that big is a bad assumption. Neglecting the vibrations in water, not a bad assumption, right? Only 1% of the vibrations are active in water. What do I mean by active? Available to store energy. So this is heat capacity. How much heat can it take in before the temperature goes up? Now that's really important in mechanical systems, like the walls of the pistons in your automobile. Knowing how much heat that wall can take before it changes its properties is important. So the heat capacity of materials is really an important thing. And now we're dealing mostly with gases in this particular case. These are all gases. But the idea is the same. Heat capacity is how much energy it can take in before the temperature goes up 1 degree. And we can see that vibrations are the real wild card. In the case of water, you totally ignore them. In the case of C60, no way, you can't ignore them. They're the majority of the heat capacity for a molecule that big. And so we'll get into using some of these numbers more in the next few lectures. And there's some example problems in the back, which I'm going to run through them here on the video so that you can check your work. But go ahead and do those example problems in the notes. Here's the answers. Okay. And here's another one. It's about 10 moles of argon. And a lot of times people forget to take into account the number of moles. Okay. And then here's the one on water. So here's the translation, the rotation, the vibration. Okay, so those are your answers for those practice problems in the notes.